Well, welcome to the second day of Stephen Hawking's 75th birthday conference. We had Russia session yesterday. Today we have gravitational wave morning. And our first speaker of the gravitational wave morning is Pablo Laguna from Georgia Tech, and he's going to tell us about kicking black holes.
Thank you. First of all, I want to thank the organizers for the honor of giving a presentation in this celebration of Stephen Hawking's 75th birthday. It's not only a tremendous honor, but also having the opportunity of listening those inspiring words that he said on Sunday about hope and not giving up. But let's talk about kicking black holes. And now that we have entered the era of gravitational wave astronomy, it's nice to start with data. Hold on, let me see if it works. Apparently not. There we go. Oh, there. All right. So this is data that, in my opinion, and I don't want to disrespect our colleagues from yesterday that were talking about the CMBR, but this is the most beautiful data that you see. Okay? And I'm a theorist. Just take a look at how the here. Just take a look at how the frequencies come together, signaling a climatic end. You don't have that in other experiments. But what I want to emphasize here, what I want to talk that is relevant to kicking black holes is the information about the masses of the binary and the final black hole. So we have one of the black holes, 36 solar masses, the other one 29, and the final black hole 67 with a spin of 0.67. Notice that information about the spins of the primary and secondary black hole is not there. And the reason is that even though the signal is very loud, okay, this is a situation in which being loud is not enough. You have to be obnoxiously loud. By that, but I mean to have more cycles, a large enough signal-to-noise ratio to be able to say something about the spins. And here on the right-hand side is some information. For instance, this is a quantity that tells you about the spin aligned with the angular orbital momentum of the binary, and another quantity related to the projection of that. So now, why is it that I'm talking about that? Well, as you will see next, okay, the way that the spins of the black hole, and to some extent the mass ratio of the black hole, the binary system, have a huge impact on how the final kick on the final black hole is determined. So give it a little bit more detail on that. Here is the same data, and superposed on that is one numerical simulation that closely matches the data. Okay. And from that numerical relativity simulation, one can use these standard formulas that involve this quantity psi4, that is a Weyl scalar. And with that, one can estimate how the energy is radiated, the angular momentum, and the linear momentum. And here is a plot of that as a function of time, angular momentum, energy, and linear momentum. Okay? So the question here is how, relevant to this talk, is how this linear momentum accumulates. You can see that there is a growth all the way to the point in which we detect the first time the common horizon, signaling that the black holes have merged. And you see some oscillations here. It's not only just a monotonic growth, and I'll talk in a second about that. And once that the final black hole settles down, you see that the emission is constant there. So what I want to do next is to first give you a little bit of a background on the early work that didn't involve numerical relativity, about estimating the kicks of the black holes, and later I will tell you the contributions from numerical relativity to the understanding of kicks. So first, the seminal paper on this, in my opinion, is in 1983 by Fitchett, in which using a Newtonian binary and just keeping the lowest order in the flux of angular momentum, realize that the kicks are the result of this beating between mass quadrupole moments and octuple and current quadrupole moments. And basically the formula that was used is the one at the top. Now, Wiseman, in a paper in '92, provided a very nice kind of back-of-the-envelope explanation about how these kicks are generated in this case. You have a situation of an unequal mass black hole. The smaller mass moves at a larger speed. Therefore, it meets linear momentum at a high rate. And even that in the spiral phase, things average out. At the moment in which the binary is about to merge, the signal basically shuts off, and that's where you get most of the recoil, which the black hole, the resulting black hole moves in the opposite direction than the emission of linear momentum. With that, you can estimate the formula of the kick that involves this function here that depends on the ratio m1 over m2, and also depends on the ratio of the total mass to some estimate of what is when you reach either what it could be the innermost stable orbit or around that, or the term in which the black holes merge. Now, what is important to notice is the following, is that this quantity f of q depends quadratic in q and as 1 minus q. So if you have two competing effects, if the binary is close to be equal mass, this term is small, okay? Because q is 1, or if you get that the mass ratios are relatively large, then this is the quantity that dominates, and you get a suppression on the kicks. So it will come back and show how this estimates match the ones from numerical relativity. All right, but before that, the next step was finding. Okay. Remember, the kick is the result of asymmetry in the emission of linear momentum. So the next way that you can do it is with spins. So Keter, in particular in 1995, presented an estimate of how the spin-orbit coupling also induces linear momentum, and roughly goes again as some quantity that involves the mass ratio. Here is a symmetric mass ratio, eta. But you have also contributions of a quantity that depends on the spins. This is a delta depends on the spin, the difference on the spins of the black holes. And you can have that the spin is generated, I mean the linear momentum is generated depending if it's along the velocity of the binary or the radial separation. So just to make an estimate of the linear momentum of the kick generated in these cases, you can then obtain just a back-of-the-envelope estimate of that by calculating the rate as a function of the energy, the rate of linear momentum emitted as a function of the energy emitted, and taking the ratio of these quantities. You get here that in one case is proportional. In the case of unequal mass black holes, is proportional to the difference in the masses, and in the other ones to the spin. So one can just calculate the kick by plugging this expression here and the estimate that the energy emitted during the merger. That is about a few percent. So with that, you know that you can generate kicks of the order of a few hundred kilometers per second, both by having unequal masses in the binary, or also to have a distribution that is not symmetric with the spins. All right, so these are estimates that just don't involve numerical relativity. They were mostly post-Newtonian. So let me just pause for a second and go back to the role of numerical relativity, not only that it has in gravitational wave detection, but also in understanding of kicks. So, and just to make the case stronger, I just very quickly show again one of the slides from the LIGO papers, in which you can see here that the red line in this case, okay, represents one of those numerical relativity waveforms that closely match the data of the first detection. All right, so here is a history of numerical relativity in 3 slides, okay? The first one that I want to show is the one of the two approaches to solve the two-body problem in numerical relativity. And that was pioneered by Franz Pretorius. Perhaps he will tell us more in his talk later on. And it's the one using generalized harmonic coordinates. But the generalized harmonic coordinates was not enough. In my opinion, this was the result of several elements. One of them is the work by Matt Chopwick, actually Franz's supervisor, about adaptive mesh refinement. Numerical relativity wouldn't be what it is today without the tools of adaptive mesh refinement. The second ingredient that I believe is that David Garfinkel, using harmonic coordinates, did a study of singularities in a cosmological setup. But that was one of the first pieces of work in which we realized that, or the community realized that harmonic coordinates could have an important role in numerical relativity. Then Karsten Gunla suggested that using constraint damping together with harmonic coordinates could be able to alleviate some of the numerical instabilities that were shown in the code simulation. So at the end, Franz in 2005, actually was in a conference in Banff, announced the results. It was very impressive to hear that after many, many years of attempts to solve the two-body problem, that was possible. And here is just a snapshot of the equations that he used. The second approach is BSSN. And BSSN was first introduced by Shibata and Nakamura in 1995, reintroduced by Banver and Shapiro. And the general idea is to go from a system of equations that involve the spatial metric and extrinsic curvature, the ADM set of equations, to one in which you decompose the spatial metric, that is a metric of the spatial hypersurfaces, into two parts, one that is a conformal factor and the other one the spatial metric, and you do something similar with the extrinsic curvature into the trace and a traceless part. But that is not enough. Actually, in grad school, I tried using that in cosmology, and without this, and you could not go too far. Okay? The key point is introducing this extra variable. To understand how that works, I usually use the example from E&M. Here is E&M written for the vector potential and the electric field. That is the one that closely mimics what we do here, with the vector potential playing the role of the metric and the electric field playing the role of the extrinsic curvature. So if you do that and decide to write a code based on this form of equations, you're going to run into trouble. Okay? There will be instabilities that will prevent you from doing simulations. And the main problem is this term. Without this term, the equations can be written in a strictly hyperbolic form. And so the idea is to get rid of this term in a sense by introducing this variable, which it plays the role of this gamma. And it's not that difficult to construct also an evolution equation for that. So that is basically the approach. So, but the equations are not enough. Okay? We have also, as we know, okay, we have the freedom, okay, of determining the time that elapses between two hypersurfaces when we do evolution, the lapse function. And also we have the freedom of relabeling the points in those hypersurfaces. And that is encapsulated by this quantity called the shift vector. Okay? So that freedom was the one that in the 90s people start exploiting. For instance, in 1995, Charles Bona started using what it was a 1 plus log slicing, that is this equation here. Then in AEI, Alcubierre and others start playing with the idea of a gamma driver shift. That is an equation, a second order in time here, in which it involves how the beta quantity should evolve in time. But the elements were there, more or less. However, still, it was not possible to evolve two black holes through merger and calculate the waveforms. It was until 2005, the paper appeared in 2006, in which two independent groups, Campanelli et al. At that time in Brownsville, and Baker et al. In NASA, that introduced one element that was key on that. You can look at the equations that look very similar. Here is this term here. The only difference is this term here that looks like an advection term, for those of you that are familiar with fluid dynamics. This other equation changes a little bit, but the idea is that you have both here B, then it's evolved here, so, and another advection term here. So this advection term, what it did, it allowed the black holes to move in the computational grid. Up to this point, the approach was to keep the black holes fixed in the computational grid. So that was a huge breakthrough, and that was 2006, and you will see that it only took a few months for all the groups, including our group, at that time I was in Penn State, to be able to do the changes that we already had in the code, implement this, and to be able to do the physics. And the codes have not changed for over 10 years. I can tell you that our code, the way that it hasn't changed for 8 years, the way that the equations are handled. Okay? So it was amazing that this method is so robust that you can do all the wonderful things that we do now in Numerical just by introducing those changes. So back to kicks. Okay? So this is now the kicks involving unequal masses. That was the first paper that I showed by Fitchett, and non-spin black holes. So we did that. Several groups did that. You see, it's 2006, the same year of the breakthroughs. Didn't take that long to do. And what it was found is that you can do several simulations for different symmetric mass ratios. The group in Jena did a fantastic work of doing a set of simulations that mimic the results that one can do with post-Newtonian, and adding to that the closed limit approximation. You can tell here by these dots that there were differences among the codes. Okay, even though we were using the same equations, the same type of infrastructure. For instance, a group in NASA got a kick here. We got a little lower kicks. The group now in RIT, they were higher. But those were mostly things related to resolution, related to the infrastructure in AMR, that it could be tricky. But at the end, I think we're able to come up to consensus, and I think most of us agree that the work in Jena is the one that reproduces the correct kick result. So what I have done here, I have used this formula for the 3 events, LIGO events, just to give you a sense of the type of kicks that you get. And the first one was about 60 kilometers per second using this, 137 and 110 kilometers per second. Now, notice here, in this plot, sorry for the labels being a little bit too small, these are how the kick accumulates. Okay? And notice that it grows, the merger is sometime here, and then you get that instead of emitting angular momentum in certain directions, you get some in the opposite, linear momentum, you get linear momentum emitted in the opposite direction. So what's going on there? Okay? Seems that there is what is called an anti-kick. Okay? And it took a while to figure out what was happening. And in my opinion, the one that came closer to understanding why you get an anti-kick was this beautiful work by Luciano Resola and others, that what in this diagram shows basically the reason behind this anti-kick. So and he did it with a head-on collision, but the same thing applies also if you are doing it in spiral. What you have is, again, this is an unequal mass system. This is the one that right the edge is moving faster. You get a stronger emission this side. So you get that the recoil goes in the opposite direction. As the black holes merge, what you get a situation is that a common horizon that is highly distorted. And it is the places where you have larger curvature in the horizon that emits stronger linear momentum. So it's represented here by this. And so now you have that the emission is stronger in this direction. The center of mass will move in the opposite direction. So he did, Luciano and his collaborators, they did a simulation of head-on collision of two actually white black holes. It also applies to the black ones, in which they were able to explain how this anti-kick accumulates and settles down. All right, the next step is kicks with spins. So in 2007, and actually it's 10 years ago, I would like to call it is the year of the kick, because that was when you will see most of the papers were published that year. We first consider the kick situation of equal mass, but black holes in which you have the spin down and the spin up. So you have this asymmetry that you need in order to induce the kick. And here is a function. Here is a plot of the kick that you can get as a function of the spin of these black holes. We consider equal spins, and you see that as you approach maximal spin in black holes, the kick increases linearly, and you can reach now kicks of about a few hundred kilometers per second. Remember before, for the unequal, it's about 140 or so. So you can go even higher. You can also get the anti-kick. You get here the situation, and the kick accumulates, and you can get the anti-kick. And what you can also see that the dominant overlap of modes that contribute to the kick is the 2 minus 2 and 2 minus 1 mode, okay? Both for the x component and the y component. So just as a reference, if you have kicks along the orbital angular momentum, what you get is that the kick is in the orbital plane. So that is still a very symmetric situation. The next step was to get more arbitrary, more generic black hole spins. So what we consider, and not only us, but again the group in RIT at that time and the NASA group, we consider spins that one of them was aligned, the other one in the orbital plane. We play with the angles and so on. And what you can see now is that you are getting now spins in the z direction, and they start getting higher, see about 900 kilometers per second. Okay. And you can see also here that the spin also depends on the separation of the binary that you start your simulation. Here is another one from the group, and this is the one for the group of Campanelli, and you get these kicks of 500. So remember, now it's one of them verical, the other one varying from being anti-line to being in the orbital plane. Now, in the summer of this year, 2007, in a conference in St. Louis, if I remember correctly, I saw Ulis there. Somewhere is Ulis. He can remind me which Ulis Perhake was the one that presented in this conference the first simulations, okay, of what is called the Superkick. Okay. It was amazing. You know, we were in that conference that you can reach kick velocities now of thousands kilometers per second. Remember, the estimates from Post-Newtonian were a few hundred, and we increased it to about 200, 400, but we didn't expect that it could reach this level. Okay? And you will see why this created a huge interest in the astrophysics community. Here is another paper by Campanelli et al. In which they vary. Okay, right now the spins had to be in the orbital plane and opposite to each other in direction. And what they did is they vary one of the angles still in the orbital plane, and that's how you get that you can get kicks pointing in one direction. You can also get the situation that in which the kicks are zero because they are orthogonal to the separation, and then you can go back to where you started. Okay. Now, playing this game, so to speak, we at that time at Penn State, what we did, okay, suppose that now, instead of having circular binaries, you have binaries in hyperbolic encounters. That is, doing that, you have the possibility of having the asymmetry stronger, the possibility of emitting larger angular linear momentum, and you can reach kicks of 10,000 kilometers per second. But of course, these situations are highly unlikely in nature. We believe that either the binaries merge almost circular or with a slight eccentricity. But nonetheless, it's an example that by exploring parameter space in a clever way, you can push the boundary of this kick velocity. Let's try to understand what happens with the superkick. That is the anatomy, as I call it, of a superkick. And in my opinion, the paper that does a good job in that regard was written by Bernd Brookman and his group. And what they notice is the following, is that the kick in the superkick configuration is dominated by the 2-2 mode and the 2-2 mode in the Weil scalar. Not only that, the two of them, as the binary system spirals, the two of them oscillate. The two of them, one of them dominates, then they become subdominant, and so on. So it is the difference that is what is important. So here I have, by plugging the psi4 scalar in the formula for energy emission, and the psi4 for that linear momentum, notice that you have basically the same factors. What the difference is that the coefficient in front of the 2-2 mode and the coefficient in 4 in the 2-2 mode, there is a minus sign there. Yeah. So you have that as you evolve, and here what I plot is that difference, as you evolve, they change roles. And eventually, once that they merge, and the merger takes here, that is where it gets frozen, and that is where the superkick gets imprinted. So you can do a back-of-the-envelope estimate, as I did for the post-Newtonian. Just basically divide these two quantities, put the energy emitted in a binary that, again, is roughly a few percent. This quantity here, just the simulations show that is typically the ratio of these two coefficients here is of the order of 0.4. And with that, you can get already the estimate that the expected kick should be of the order of a few thousand kilometers per second. All right. So now, what would you do with that? Okay. Still, even today, simulations are very expensive. Yesterday in the reception, I was talking with Harold Pfeiffer about how long his code takes to run simulations with relatively large separations. And some of them can take half a year. Okay? For us, the same thing. Typically, exploring parameter space is a month. All right. So it will be unlikely that we're going to be able to just do simulations on demand if the discoveries start taking place at a faster rate. So the option that we have is to be able to, as a community, get together all the information from the runs and create, okay, either phenomenological or effective one-body waveform models. That is, models that are parametrized in which the coefficients or the parameters are fixed by numerical relativity. You can also do these fitting formulas of the final speed, mass, and kick, and these coefficients here are determined by the simulations that the community generates. Well, that has happened with this. There are very good estimates of fitting formulas for the final speed of the black hole, the final mass, and the kick. And with that one is what you use to do astrophysics. Okay. Now, let me just spend the last few minutes talking about the consequences of the kicks. If you're talking about the unequal mass kicks that only go to about 150 kilometers per second, what I'm plotting here is the escape velocity of some structures in nature. You have globular clusters, dwarf spheroidal, dwarf ellipticals, and so on. So you can see that the escape velocity of black holes living or inside globular clusters already are much higher than the escape velocity of those objects. Okay. If you go to the superkicks, it translates to the fact that a black hole with a superkick will likely escape even an elliptical galaxy, one of the most massive galaxies in there. So, and that is a problem. Why? Because we observe that almost all galaxies host a supermassive black hole. So how do you avoid having the situation in which you observe supermassive black holes, but at the same time you have kick velocities that are 1,000 kilometers per second? Well, the solution is that you estimate, okay, what is the likelihood of having those kicks. And the likelihood of having those kicks depends on the environment. There was a paper by Bogdanovich and Cole-Miller that showed that if you have a binary system in a circumbinary disk, likely the black holes at time of merger will have the spins with orientations aligned or closely aligned with the orbital angular momentum. So in this recent work by Bleccia, what they did is they worked the two situations, the two extreme situations. The spin aligns with orbital angular momentum because of the torque from circumbinary disks, and the spin orientations close to random. And those models, they have one that is called hot, another one cold, and they have the random model and the model in which you restrict the alignment to be 5 degrees with the orbital angular momentum. And what they find, not surprising, that if you have a 5-degree alignment, okay, the ratio of the kick velocity to the escape velocity is always less than unity. So you have that the black holes remain in the galaxy. If you have a situation in which you have a gas, but the gas is not very effective in aligning the spins, you can have cases in which the supermassive black hole escape, but still most of them are bound to the. And here are the cases in which you have a random. Yes, if the situation is in which you have random accretion or you have collision with the stars, in which when you enter the merger, the black holes can have the superkick configuration of anti-aligned spins, you have the possibility that the black holes are ejected from that. Let me just finish by talking about the detectability of a recoiling black hole. Okay? So in a case of a supermassive black hole, if you have a recoiling black hole, what it will do is, this is exaggerated, but it will carry with it parts of the accretion disk. The estimate says that that accretion gas will be accreted for about 10 to the 5, 10 to the 6 years, and it will look like a quasar-like object. Okay. It will travel away from the center of the host galaxy, so you should be able to, in principle, see an object that is quasar-like displaced from the center of the galaxy. And if things are favorable, it could even capture more gas and continue shining that way. Okay. So what do you do to detect that? Okay. One way is you go and look if there is a quasar that is spatially offset from the center of the host galaxy. One way. The other one is if you have the broad emissions from that, from the black hole with this disk that carries with it, had different velocity from those emission lines from the host galaxy. However, okay, the challenge here is that even if you see that there is a quasar-like object displaced from the center, that doesn't mean that it came from an ejection. It could be that it was a result of, for instance, a merger of galaxies, and there still has not settled down. So that is what. The other thing is that the broad emission lines are notoriously asymmetric, so it's difficult to measure this velocity shift. So let me just show two examples. This is one recent in which here is the center, and this is the displaced object. Okay, so there is the HST image shows that there is an offset from the center of the galaxy, and it's difficult to see here, but they were able to look at broad emission lines and measure a displacement of about 2,000 kilometers per second. So this will be a superkick type. And the other case is one that Stephanie Comosa in 2008 presented as an example of a kick black hole or recoil black hole by looking at the blue shifted lines and estimated that it was coming from a black hole about 26 kilometers per second. There was a competing interpretation of that, in which perhaps it was still a binary system in which you can also get this type of displacement. A recent paper showed that those lines that hinted the presence of a supermassive black hole recoiling was not the case, because they detected other lines coming from this galactic scale molecular gas reservoir. So the bottom line is that it is a tricky business, but I think that doesn't mean that one should give up. I think there could be a case in which is the smoking gun. And also recently, a paper coming from people in this place, here in Cambridge, in which they say, look, you can even attempt measuring kicks even if you don't go and look at electromagnetic signals. What happens is that at the moment in which the kick gets generated, there will be a blue shifted or red shifted mass in this part of the signal. Then if you're able to make an estimate during the spiral about the masses of the colliding black holes, and you will see that that mass doesn't give the same total mass at the merger, and by looking at that difference, you can make an estimate of the kick. However, the problem is that the signal-to-noise ratio that is needed is quite large for LIGO. Perhaps for LISA will be doable. All right. Let me just conclude with just two remarks. Okay, not surprising, gravitational wave astronomy is here. And numerical relativity is truly a tool of discovery now. It's helping not only with the interpretation and the detection of gravitational wave signals, but I think one can use the information from numerical relativity also to unveil interesting astrophysical effects. And black hole kicks, even with the challenges of detecting them, or the challenge of getting data clean enough to say that a kick has taken place, it's an exciting candidate for doing multi-messenger astrophysics, or multi-messenger in the sense that one can combine information, perhaps not in the same event, but information coming from electromagnetic observations with LIGO observations. Thank you.
Okay, do we have some questions for Pablo? Actually, I have one.
All right.
So that last slide you showed from Chris Moore and I'm not sure, David Grosser, wouldn't the numerical relativity simulations already have these effects in them? Because, you know, for whatever kick you have, it's going to shift it in a particular direction. So, I mean, I know it's particular for the configuration that it finally plunges in, but wouldn't you have to take these effects out when constructing the hybrid waveforms and that sort of thing? Because isn't this going to be in your signals?
It should be there. Definitely should be there. And actually, that's one of, I mean, the paper is very recent. I think, I don't know if, let's see, if Uli is here. If he has looked, have you looked into your?
Yeah, so I've been pondering on that point. Oh, thank you. Does it work? Yeah. I've been thinking about this point for a significant amount of time, and I've been discussing that back and forth with Davide. And actually, initially, I was a bit discouraging to them, I think. Because you're absolutely right. This is in the numerical waveform, period. However, and they convinced me that's not quite the spirit here. The idea here is not to call into question the numerical relativity waveforms, but to identify a purely observational signature in the gravitational waves that tells you about the kick. Now, of course, there are two approaches here. One thing is you identify the optimum parameters and then go to your numerics and redo it. However, I think you need such a precision that it's virtually impossible, I think, at least in the foreseeable future. So what they do here is different. They say, okay, let's really forget a bit about numerics. Let's consider the inspirer that we can model somehow using numerics, post-Newtonian, and we get a wave signal, we get parameters. That should certainly give us, with a fairly good deal of precision, the mass. Now let's go to the ring down part of the signal that is definitely post-kick accumulation, and therefore you should have a different mass because you have the blue or red shift. And that is sort of the one weakness we still have in this case with the LIGO, and that's precisely the thing that Pablo mentioned, that you need a fairly high signal-to-noise ratio to get a good estimate for the mass value post-merger. But with LISA you could do it. And then you simply have two different mass values. The fact that numerical relativity exists is almost immaterial at this stage.
Yeah, but I mean, maybe turning this around, it seems like this is a potential concern when you're trying to construct very accurate hybrids of numerical relativity waveforms, because if you don't take into account the effect in the numerical relativity waveforms, then for a different, a slightly different plunge location, you're going to get the wrong waveform. So it seems like you have to remove this, otherwise it's going to be like a systematic error in the high precision matching waveforms.
I don't think so.
I don't think it's about removing. I mean, it is there. I mean, the effect in every simulation is there. So to me, if you're able to have enough signal-to-noise ratio during the spiral, numerical relativity is going to tell you what the kick is by itself. Okay? Because you can even just go and plug that into this fitting formula and so on. I think is what Uli is saying. If you just go and do the estimate from the ring down and in spiral, and from that one you try to infer the kick. That is the difference in this approach. Yes.
There's a question up the back here.
I have a comment about your breakthrough method for dealing with moving punctures.
Yes.
It seems very similar to Lagrangian coordinates, where if you jump on the fluid, you can reduce the equations from a system of partial differential equations to a system of ordinary differential equations. And the geometry for that was already described 30 years ago by Vladimir Arnold, and it was described by Eben and Marsden analytically about 30 years ago. And that's very similar to the method that you're using. You're simplifying your equations by essentially using Lagrangian coordinates, where the spatial terms disappear when you move with the fluid.
It's not quite like that. It's not quite like that. We're not going, actually, the approach, and perhaps Harold will tell us a little bit more about, the approach that they use in harmonic coordinates in the Cornell-Caltech collaboration is more about going into this co-moving frame,
yes,
in which you factor out longer time scales from a short one. For us, it wasn't that. It was that we were using the freedom of relabeling, the community was using the freedom of relabeling the coordinate points to keep the location of the black holes constant. Actually, the first orbit by Bernd Bruckmann, that's precisely what he did, and it was a tricky business to keep him there. What actually we did with these advection terms is to let them go. So it's more going into, if you want to put it that way, more into an Eulerian type of description in which you just let the flow go. Don't go into the co-moving frame of the flow.
Well, okay, that's Lagrangian frame.
Right.
The Eulerian frame is when you have the fixed spatial frame. And by just neglecting the convection term is essentially going to Lagrangian coordinates.
Right, but we did the opposite. We actually put the advection terms in.
Oh, well, then you make the equations worse. More complicated.
Well, we can talk about that because that's how we actually managed to collide black holes.
Seems to work. Okay, well, we have to move along. Let's thank Pablo again.
Thank you.